So we have two introductions today. So we have a chair of the session, the guest of the session. So welcome to this week's weekly colloquium at the School of Astrophysics. We have Professor Shubhabruta Majumdar from the Tata Institute of Fundamental Research in Mumbai as the chair and the guest of the session today. So Shubhoda, some of you will be happy to know, was an alumnus of St. Xavier's College, Calcutta. We have alumni from St. Xavier's here, more than one. And then Shubhoda was a PhD student in the Joint Astrophysics program. So officially, I think he was a student at IIA, and his official advisor was Professor Piyushpali Bhattacharya. But he spent most of his time in RRI. I don't know what was there. Maybe we'll never know. But he mostly worked with Professor Vimanda there. And after finishing his PhD, he did several postdocs, most notably with Professor Joe Moore at UIUC and also Joe Silk, right? Right.
Actually, it's Sita with Big Bond.
Right, Sita with Big Bond, yes. So, so after that, he came back and became a faculty member at TIFR. So, Shubhoda is an expert on both cluster physics and also using clusters for as a tool in cosmology. I hope some of you remember at least one slide in our class slides where cluster cosmology was one slide. So he's an expert on that. And he has been a speaker in our colloquium, and we hope he will be in one of the future ones. But today we have brought him as an opponent to to our speaker, the other Majumdar. I'll introduce Annesh now. So Annesh was a BSc student at Presidency. He joined in 2014 and finished his BSc in 2017, and then continued as an MSc student up to 2019 when he finished his MSc, and then went to the Anton Pannekoek Institute, API, in Amsterdam, where he worked with Mike Weiss, who is also an expert on X-ray observations of clusters and its interpretation. So after finishing his PhD last year, Annesh went to University of Waterloo, where he is a postdoc, and he's working with Brian McNamara, who is also a very well-known figure in cluster physics. So Annesh actually is one of our illustrious students. He did a lot of he did well in the exams, but also did a lot of research while he was here. He also probably as a result of all of this, he was selected he got PhD offers from 3 different continents, one in Ayuka, one in Amsterdam, and one in North Carolina State. And so he chose the in-between one. He decided not to cross the Atlantic at that time.
Absolutely, yeah. Way better than
We don't judge. But after his PhD, he decided to cross the Atlantic and went to Canada. So okay, so we'll hear from Annesh now, and I'll leave at 3:45. So maybe the question answer session will not be chaired by me. But since Shubhoda is here, we are hoping a lot of very, very insightful and probing questions that Annesh has to answer.
Thank you. So, yeah, just Shubhoda, do you want to say something? One more connection to Presidency, that currently our first PhD student from Astrophysics of Presidency University, Gujarani Chaudhary. So, Professor Majumdar was an external examiner in her thesis, and now her postdoc mentor. So, she is now an NPDF postdoc at TIFR after she was at Hong Kong University, and Professor Majumdar is her mentor. So there's a lot of Presidency connection. If you want to speak a few words before.
Okay, this is.
No, that's okay. That's good.
I have one more connection with Presidency.
Yes.
I have one more connection with Presidency. When I was doing my BSc in Xavier's, my practical exam was in Presidency. And unfortunately for Xaverians, the presidency practical exam was not in Xaverians. So there was no balance.
And there was always this fight.
So and that was year where it was very interesting. So I remember over here in the practical exam, the first boy got some 51 in practical. But we had a very good batch in general. So actually that year, 7 out of the first 10 students were from our place over there. But the practicals was like.
So I remember our part one exam, the written exams seat was in St. James.
But there they don't ask me. Anyway, so I mean, okay, so I mean, this is Amnesh's day, so Amnesh should speak. You guys, if you want to chat with me anytime after the talk, feel free, come ask questions or tell me what you do, or ask me what I'm doing, or ask anything in general. I'll be happy to chat. Okay, so Amnesh.
Thank you.
So,
Yes, right.
okay, thank you very much for the kind introduction. I'm not sure how well I did in exams, but I tried to do better in research. Anyways, so it's very good to see you all, come back to talk to you. So today I will be talking about some a brand new telescope that is there in the X-ray sky called XRISM. I'm going to talk about like why we are excited about it. But before I tell you all the results and why we're excited about it, I'll build step by step as to why we are interested about clusters, like why clusters are important, why are we even bothered by it and them, and like why are we excited by the results from XRISM. So to understand first, we must ask ourselves questions: what are even galaxy clusters? Some of you may know, some of you may not. So if you point an optical telescope like Hubble or JWST to a cluster, what you would see is something like this. It's like a bunch of galaxies, well, clustered together by gravitational forces, and hence the name comes hundreds of galaxies. Hence the name clusters of galaxies. But what you don't see in optical is that it's just not this in clusters of galaxies. There's a lot more matter in there, in the form which you can see if you point it in X-rays. That matter actually glows, and that matter is a lot more, about 3 times more than what you have in galaxies, in the form of galaxies. All right, and the rest of the matter is something in the form of dark matter called, which we won't care about in this talk. But these clusters of galaxies are really massive. They're about 10 to the power 15 times as massive as our sun, and they're about, can get as big as a megaparsec, which is about 3 million light years for who don't know what megaparsec is. The distance between the sun and the Proxima Centauri is about 3 light years. So that's like 1 million times more. So like really big. But why are clusters of galaxies like this? Why do they glow so much in X-rays? Well, to understand that, we have to understand how do they form really. And their formation history is really embedded in like very early universe. If you see the last scattering, like the really early universe, what you would see is something like this, where like tiny fluctuations of light in microwave, that is really due to like small matter fluctuations in the early universe. Now, if there are like small matter fluctuations, what you know, like gravity tends to do is like make everything try to collapse, because that's the only job of gravity. So it's really this tiny fluctuation that are like the seeds of everything that grows. And if you let those tiny fluctuations grow over time, they first collapse in sheets, followed by filaments. And then if you give it enough time and time, it will eventually form like node-like structures where given enough time, clusters will grow. So it's really this, that with the help of gravity, these clusters of galaxies grow really massive. And this also gives you the clue how they get really hot. If you collapse something in the form of with gravity, well, virial theorem says that a part of that energy must be released and will be thermalized. All right. Now, exactly how that gets heated up is more complicated process, but energetically speaking, that's what is happening. The potential energy is heating the gas and making it hot, really. After it has done all this collapsing stuff, what is really happening is that the gravity is trying to make it collapse, and the gas is trying to make it, well, not collapse. It's a gas pressure. So at the very basics, it forms a sort of an hydrostatic equilibrium where like you'll have a higher density at the center and a lower density at the toward the outskirts. So clusters can get about like 10 to the minus, typical densities are those, and it can get up to like a few keV, up to 10 keV hot clusters. But if you have taken a bachelor's level astrophysics course, you might recognize this picture. Well, you might recognize, well, this is just a star, right? So are clusters of galaxies just really stars? Well, hold to that on that thought. So to understand that, whether they're really stars or not, so I will show you this plot. So what is plotted here is just
the laser will work, not the slide changes. The very bottom.
So here, like various objects in the universe are plotted in terms of their density and how hot they are. All right. So about stars, well, our sun, the solar atmosphere is about this dense and about this hot. The solar corona, which is like the diffuse plasma around our sun solar atmosphere, is about here. The core of the sun is about this dense and about this hot. And if you look at clusters of galaxies, they are way over here. All right. So clusters of galaxies can get as hot as the solar core, but they're about like, well, 28 orders of magnitude less dense or something. And this is like, you see like why clusters of galaxies are so like fascinating, because they are like really unique plasma physics laboratories. You cannot make these conditions anywhere in the lab. Forget about lab, even the universe doesn't make them. All right, these conditions. So if you want to probe plasma physics, these are like really the most extreme conditions. All right, and hence this is very exciting. These are exciting objects. Now we know more. Let's know more about clusters of galaxies. Well, the gas around the clusters of galaxies is commonly called intercluster medium, and because they're so hot, almost everything is ionized. It's mainly composed of hydrogen and helium, which is like completely ionized, and it has various metals from carbon to nickel in various ionization states. Now, if you have taken a bachelor's level electrodynamics course, you know what happens if you keep charged particles around, right? They start to interact with each other. And if you have taken a master's level course, you would know that when they interact, they also start to radiate stuff, all right? So what generally ends up happening is that they start radiating in bremsstrahlung radiation, it's called, all right? And because they're like ionized atoms, they also do line emissions and combinations. Now, if you radiate, it obviously going to cool. Whatever energy is there, it's going to start losing. In fact, you can show that it will lose almost all its energy in a certain amount of time, all right? Now, this equation is nothing but just saying how much energy is there in the gas versus, and the bottom is like how much energy it will radiate. You see there's like square of the density down here. So the denser it is, the more it will radiate, shorter the cooling time. All right. So at the center, it should radiate much more compared to the outskirts. In fact, there will be a distance below which the cooling time would be below the age of the universe. And then like you have a problem. All right. If the gas radiates away all its energies, well, gravity would start making everything collapse again. All right. So you might immediately recognize that there must be an additional energy input to keep everything balanced. Otherwise, everything is just collapsing. Okay. What are those energy sources has been one of the fundamental studies over the last 20, 25 years. All right. One of the ways they do it is, well, okay, you have two balls of clusters. Well, they can just merge. All right. They can collide with each other. They can merge. All right. And they can form a shock front. Very basic. Energetically speaking, it adds about 10 to the 64 arcs of heat, all right, which is a lot of energy. Now, a head-on merger can increase the temperature by a factor of 2 to 3. And not only that, now this energy is being, only a small amount of energy needs to be go to the core to like balance it. All right. So about like, if you then generate like 0.1% of the energy, 10 to the 64, that's enough to balance the cooling generally. So one of the ways is like, if what happens if you merge, that's one way you can keep the clusters warm. But the other way is more fascinating. Is you see a fascinating picture of a cluster galaxy called Hercules A. What is happening here is that there is a black hole at the center of this cluster of galaxy. All right, and that black hole can radiate power, an enormous amount of power, up to 10 to the 46 arc per second. And what is happening here is the black hole can shoot jets, and it can physically push the gas out of the clusters. It can add energy. It can disrupt the gas. All right, and this is another one of the more interesting ways where how clusters keep themselves warm. Okay, so we have these two important mechanisms by which clusters of galaxies keep themselves warm. I will focus mainly on in these talks on how the black hole keeps it warm. All right. So how do AGNs, like what have we learned in the past 20 years? How do AGNs keep themselves warm? All right. So when these AGNs produce these jets, they push the gas out of the clusters, and they produce something called this type of structures called cavities, which are nothing but low density regions that has been created because the gas has been pushed out. And if you have a low density region around a high density region, Archimedes' principle says it must buoyantly rise. So they can rise, and as it rises and the density drops at the outskirts, it can then expand. So it can so what bubbles and cavities can do is transport energy from the close to the AGN to outskirts of the clusters. All right, and this is like a very effective mechanism by which they can spread around energy from the AGN. Well, generally bubbles can transport like a factor of few times their density before they can. I mean, it's definitely the cooling radius, like the say 100 kiloparsec or something. But some. Yes, I mean by outskirts here, I mean yes, that I loosely use the term here. It's mainly around the cooling radius and like around it. Yes, 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 yes.
So you mean they are still within the cluster?
Yes.
The cluster is
yes. Yes.
But here it will be the biconical kind of thing. It won't be like the way you saw like a complete spherical kind of thing.
No, yes. Yes, this one is yes. This is like two pairs of cavities just buoyantly moving away and releasing their.
Explain the homogeneous energy distribution in the cluster.
No, like not by themselves, but like they can like also. Well, they can also like when they expand, they can also produce shocks by themselves, which can then also then. Yes. Well, I mean, if you have a high pressure bubble and that expands, that will drive a shock as well. So, that is one way shocks can produce. They can also be produced by the jets as well. Like if you have jets can produce a very high. So cavities are one way. Jets can themselves produce a very high pressure conical region in the clusters, which then sheets. Well, there can be ghost cavities where it's like the jet used to exist in that direction. Yeah, but there it's not anymore. So you can see like ghost cavities around which doesn't have a radio bubble. Generation. Yeah. Well, not only around present direction of the radio jet. Yeah. So they, AGNs can also, the jets can also produce like shocks, all right, which can heat the cluster, as well as there can be like sound, like there can be like rippling motion with shocks, all right, which transonically moves, which we call the sound waves, like we see in Perseus clusters, where like there's like clear surface brightness ripples. So these are mainly like the three types of processes which we have understood over the past. There are a few more, but let's say these are the three many very famous processes by which AGNs have heated galaxy cores. Now, these heating is very effective. If you look at plots of, you cannot see here. So this is how much it is cooling. The cluster is cooling in the x-axis versus what is the cavity, how much power is in there in the cavity. All right. And there's like a very tight relationship between the two. So this heating is actually very effective in like just balancing the cooling in the cluster. So what is happening is that gas cooling is critical to feed the AGN, but then the AGN produces cavities and shocks that is just enough to prevent the ICM from cooling down. All right, and now how do AGNs, which are like very small, have this effect over 100 kiloparsec? Has been one of the critical studies of the last 20 years. And observatories that have critical in this study have been Chandra and XMM. And they have been like big leaps over the previous generation of telescopes. They have high spatial resolution, which about 0.5 arcsecond for Chandra, 8 arcsecond for XMM. And they are very critical in detecting shocks, cavities, stuff like that. They are also a big improvement in terms of the effective area and their lower background, which allows us to do a more complete exploration of the background, including like more farther away from the cooling region, which are not possible with, say, Einstein or Rosat. Their spectral resolution is good enough that we could measure the lines of individual elements very well, so that we could measure the abundances. And studying abundances can tell you where did they come from, like what is their origin. As well as their spectral sensitivity. Like, it's the first time we could do from 0.1 to 10 keV spectral sensitivity, which allowed us to better measure the temperature. With Einstein, you could only measure up to 5 keV. With Rosat, you could only do it at 2 keV. So Chandra and XMM were like revolutionary in this respect. Right? But this is all like overview theory and like abstract. Like, how do X-ray specialists, like the picture I told you before, how do X-ray specialists come up with that picture? Well, they come up with like spectroscopy with Chandra. What you are seeing is a real spectrum of a real cluster that I've been working with in the past few days. So this is not some made up stuff I'm showing you. All right. So this is a Chandra spectrum of Centaurus cluster. You can immediately see, like I said, like you can see the individual lines are very clear in the spectrum. How do we figure anything out from this spectrum? Well, first what we do is we check the normalization of the spectrum. And if the density is higher, then the normalization would be higher. If the density is lower, the normalization would be lower. So checking the normalization would tell us the density. Checking how strong the lines are would tell us how much the abundances are of each element. How much the wider band allows, the shape of the spectrum tells us what the temperature is, and various charged states of the same element tells us like what is the state of the plasma? Is it in equilibrium or not? All right. So once you have these quantities, once you measure these quantities from spectral analysis, you can then use basic physics equations from your bachelor's level, master's level to say what the pressure is, what the enthalpy is of the cavities, what the entropy is of the gas, how much heat is being added by the AGN with respect to some baseline entropy, and finally, what is the mass of the cluster with radius. using hydrostatic equilibrium. The whole picture I told you, you can construct using just spectroscopy and basic physics equations. All right, and this is how we do it. And this is how we have done it over the last 20 years. But okay, but what then XRISM adds? All right.
So, can I ask a
Yes.
question? So, the slide you were getting the mass by using the hydrostatic equilibrium condition. But you know, we have this hydrostatic mass bias. Are you going to talk about that?
Yes, I'm going to talk about it. I'll show you it in the cluster core. At least it doesn't matter anymore. I'll tell you. All right. So why is XRISM important then? Right. Well, I can tell you or I can show you. So this is the Chandra spectrum. Ready? This is the XRISM spectrum of the same cluster. All right. What you immediately notice is that there are way more lines than you ever saw before. These lines that you previously saw with Chandra were actually blending a lot of lines together. All right. Silicon has silicon 14, 15, 16. Sorry, silicon 14 and 15. There's a sulfur lines, argon lines, calcium lines are all mixed together. You can see, and the iron lines are actually, I'll show you later, are actually 4 sets of lines, this iron K. All right. So immediately the progress is clear that we can see way more lines, and it will help us to allow us to know much more about the plasma conditions.
On this question,
Yeah.
if the iron L line is not in the field, or you
No.
cut it off, or
No. So yeah, this is a very good question. So we cannot see below 1.7 keV with XRISM because of, unfortunately, there's a gate valve in front of XRISM that was supposed to open. But after the launch of the XRISM, we could not open it. So the gate valve, there's a beryllium gate valve, which absorbs everything below 1.7 keV.
And why is it
Which one?
the continuum
Yeah,
below the lines?
I think
For
there's,
the Chandra, it sort of goes up.
yes.
Here
Yes.
it sort of curves down.
This is, I think, because of the effective area shape you were seeing. So like
So
this is,
fully unfolded.
yeah, this is effective area folded. Yeah, because like this one rapidly goes to 0 below 1.7 keV. All right, while Chandra is more sensitive even below that.
Physics.
Yes.
Then the crucial question is, do you have all the physics in hand that affects each of these lines separately?
Okay, so you.
And, my naive opinion is that we don't. So can you sort of justify this? Because we are talking about splitting of lines. Small, and then your physics will tell you how much of this density is more than this density. Do you have that physics in the model that goes in?
Yes, we do. We can calculate spectrum exactly based on what not only the density, temperature, and abundance, based on what should be their gas motions, what should be their charge states, whether they're in equilibrium or not, and we can predict spectrum. All right, and then we can fit it with the observed data.
Hyperfine small transits. Can you do that?
So yes, okay. So this is, one of the advances of XRISM is also making is in the atomic physics subject. All right. So we have a pretty good understanding, and I will show that we can do those lines pretty well, but there are still differences that we are still understanding. Those are pointing to new atomic physics that are not taken into account into our model, because maybe we are not taking into transitions from every other state or something. And so it is also improving our atomic physics knowledge as well. So it's doing both. But is that the question you asked, or?
I'm just asking, like, how confident we are about.
Oh, we are pretty based on like the fits we have done. We can match it pretty well, but not as well as we would like, because we would like to match everything. That's not happening yet, but we are still studying why that is. Is it because of our atomic physics knowledge, or is it because some physical condition within the clusters that is we are not taking into account? That is still, people are still exploring.
There is something to constrain.
And people are doing that.
say that see, you are all solving all those equations you have written, and only you are adding more species to it, or doing something else, something more.
So there's some, on top of those equations, you also have chemical equations.
Chemical equations.
Well,
chemical
so those equations I showed previously, those are like after you fitted it. Like during fitting, what you only do is like balance the Shah equations and stuff like that. So to get and statistical equations to just get the ionization states and then predict the Bremsstrahlung and line emissions. Yeah.
You are not adding new physics to it. Only the number of
Yes.
species you are adding to it. Right?
Number of species. Yes, yes, yes. Yes.
Say, if I think about the atomic physics,
Yeah.
right, the ionization states of the elements, and you're talking about the Saha equation. So when people model this, do they completely rely, because Saha equation is an equilibrium statistical mechanism. Also want to add non-equilibrium.
So we have models for everything. So like people have done equilibrium models, which in spec it's called APEC. In the specs it's called CIE, collisional ionization equilibrium. But there are also non-equilibrium ionization models that we can fit. Like if your equilibrium model in clusters, we expect it to be in clusters, at least in the core, we expect it to be equilibrium. But if there's a shock, all right, we expect it in non-equilibrium, and we can fit those non-equilibrium models to get parameters. So yes, people have you have to just drop the equilibrium assumption.
Is the spectrum of how much big of the cluster, the entire cluster?
I'll show you. So this is my 3x3 arc-minute footprint. And then it depends on like the redshift of the cluster. So all right. Okay. So the advancement is that the energy resolution is about 5 eV. All right, compared to few 100 eV with Chandra. All right, or XMM. This is at 6K eV, by the way. And there are like far more ionization and excitation states visible that I told you, and which we can constrain more of the plasma physics. So now that I showed you, now I want to tell you now what about XRISM. All right. So XRISM stands for X-ray Imaging and Spectroscopy Mission. That's what XRISM is, if you wanted to know. So Resolve has very high energy resolution. So Resolve is like this instrument. The telescope looks like this, if you're curious. Resolve looks like this. The Resolve has a field of view of 3x3 arc-minute. So the diameter of the moon is like half a arc-minute. So like 6 times that. Okay.
Half degree.
Oh, sorry. Don't worry then. Okay. Sorry. So, and there is, along with Resolve. So Resolve is the one that the spectrum I showed you. All right. And that's the instrument we'll be mostly caring about in this talk. But there is also an extend instrument, which is a standard CCD, which is like Chandra detectors. People use extend because it is a very high field of view, 30 by 30 arc-minute, so it's massive. This is the diameter of the moon. All right. Okay, and it has a very low background, so you can really explore cluster outskirts with this instrument. But we will be talking about Resolve mostly. So why is Resolve so much better than previous generations? Because it uses a principle called calorimeter, really. So what happens is that you have a heat bath, which has been set to a very low temperature. All right, and what happens is that X-ray photon comes and hits that absorber, which is connected to the heat bath, and it causes a really small change in temperature. And we can measure that temperature, all right? And this temperature, we can measure it very accurately compared to CCDs, where what happened is if X-ray photon hit the CCD, what it created was an electron-ion holes. And so what you needed to measure was charge, like how much charge it has given up. All right, and so technologically speaking and conceptually speaking, it is much easier to measure how much change in heat was versus how much charge, reading out the charge and measuring how much it was, right? And this is pretty much the reason why calorimeters, like we can measure it much easier compared to CCDs. The working principles are quite different, right? No, yes, so good. By resolution, you mean spatial resolution. So I will show you, all right? So just the next slide, So when I talk about high resolution, it's about spectrum, all right? When people mostly confuse because people say, oh, well, you have a high spectral resolution stuff. You can just point it at any part of the cluster and get a really good detailed stuff, all right? So Cygnus A looks gorgeous in Chandra. In XRISM, it looks like this, all right? And for two reasons. One is that we have only 36 pixels, all right? So like it's going to be come out pixelated no matter what, all right? But also the point spread function is really big, all right? Really broad. I mean, the FWHN is about 0.9 arc-minute. So it really blurs everything out, okay? 0.9 arc-minute. So it's slightly less than 60 arc-second. It's just, yeah.
Now, even this extra addition, how confident are you that you're going to separate out different spectral lines?
So you mean
Because now
yes.
physics of
Yes, that's a very good question. So I didn't want to go this technical, but okay. So you have to use the spatial information from Chandra to constrain, so what we do is a spatial spectral mixing, what is a technique called. So we use Chandra image to calculate how much scattering is coming from the outside. So let's say you have extracted spectrum from this region, all right? Using Chandra image and the PSF knowledge, you can calculate how much scattering is coming from outside, how much is being scattered away from inside to outside, and all of these calculations. And you can create ARF, which is like area response files, all right, for individual scattering, and then fit simultaneously. That will give you the knowledge of plasma conditions of both outside region as well as inside region. So we are using Chandra, using the spatial information of Chandra and combining with the spectral capabilities of XRISM.
I guess, let's say you have equilibrium and non-equilibrium. In the shock, you will have the non-equilibrium thing, and other places, yes, you need to be equilibrium. Then how can you distinguish there? How much part is in equilibrium, how much part is in non-equilibrium?
So this is a very good question. So yes, so it depends on whether you can separate it out, depends on your exposure and stuff like that. All right. But the real question is, right now, XRISM is, because it has lost its soft band and stuff like that, we are mostly focusing it on the core of the clusters. Okay. And in the core of the clusters, mostly the things are in equilibrium. So the studies that have been done so far considers equilibrium. So we can go add more complexity if we move outside the core, but that is more complicated, as you say, and people are still working through it. But I must say, because
I am happy with as long as you are getting more and more spectral.
Yes.
I'm not at all arguing.
Yes.
It is always better to have.
So the hope is that Athena will do both.
Yes.
You do both spatial
Yes.
and energy. But Athena's budget is shrinking, so who knows what to do.
Okay. All right. So bad angular resolution, good spectral resolution. If you want to get spatial information, use Chandra to combine with XRISM. All right. Now, so why high resolution? So I just showed you that it has more lines, but more lines is more complexity. Like, who wants that? All right. Why would we even care about high resolution spectroscopy? Well, the reason is that it's not just shocks and stuff we had to study. The thing is, what AGN does, it directly impacts the ICM by inducing gas motions. The jets ram into the ICM creating shocks, which creates gas motions. All right. And then these gas motions eventually dissipate into the heat that you can see in like spectrum. All right. So we want to study this entire pathway. All right. The gas motions, unfortunately, cannot be detected with Chandra and stuff like that because, so with XRISM, we want a very good spectral resolution because XRISM shows an average motion. So everything has been blurred. All right. So even though Cygnus A has like 2,000 kilometers per second shocks moving, if you average it out, it would only be a few hundred kilometers per second. And you want the spectral resolution to be able to see that. Previous generations were like few thousands of kilometers per second. Okay, but you say that's problem with XRISM. Maybe throw away and bring a better telescope, maybe? That's not an argument. Okay, but like there are more things that we want to study. It's not just the average gas motions. It's also something called turbulence in clusters of galaxies, all right? See, when bubbles rise up through cluster atmospheres, they can create like wake-like structure, like as the atmosphere sweeps around the bubbles. And these wakes can create these things called eddies, all right? Eddies are like, you can see like swirling vortex-like structures, not exactly vortex technically, but like you can think about that. These eddies can have certain energies that have been given up. These eddies can like shear and turn into smaller eddies, all right? And like they can become smaller and smaller until they have dissipated their energy. In fact, I can show you like more, let's say you have injected some energy at some eddy scale, all right? Through shearing and shearing, the eddies will speed up. Sorry, the eddies will speed down as it becomes smaller and smaller and smaller until they are dissipated into viscosity, all right? So nu is the viscosity. Depending on how large the viscosity is, you can determine how small the eddies will get before they're like dissipated, all right? And so this transition from like a large eddy to smaller eddies and eventually dissipating is called the energy cascade. And in classical turbulence, they follow a relation called k to the power minus 5 This is called Kolmogorov turbulence. K is the wave number, so like how big it is, inverse of that, all right? So generally, classical turbulence follows this pattern. This is how you inject something at a large scale, it then becomes smaller and smaller with eddies and then dissipate. Okay, so what we want to know is turbulence an important process even? All right, like is turbulence important? Like can turbulence by itself offset cooling in cluster cores? Then it needs to match the cooling rate. Can it travel fast enough? It needs to reach the cooling radius. All right, need to heat all the cooling radius. Okay. And is it Kolmogorov in shape? Needs to obey the 5/3 dependence. For Perseus, you'd need about 700 kilometers per second to like reach that all the cooling radius. Okay. And here was a high resolution spectrum. Which one? This is like turbulence. Velocity dispersion. Dispersion. Yes, this is a velocity dispersion. Yes, technically it is so like you'd have. Yes. So yes. And here that high resolution spectroscopy really becomes important because depending on how wide the lines are, you can determine how what is the velocity dispersion. All right. So 100 kilometers. So this is from a XRISM proposal we wrote, which we got the time. So and this is like if the lines, if it's only 100 kilometers per second, you can see the lines very clearly. And if it's 600 kilometers per second, all of this is blended. So to distinguish like hundreds of kilometers per second turbulence or gas motions, you need that high resolution spectroscopy. So
this turbulent velocity, not the way this
not bulk motion. Not bulk motion. This is, it can be unresolved bulk motion. All right. So like if you're throwing line of sight, all right, and like if it has like a solid sphere like expanding, it can broaden the spectrum as well if like it is unresolved. Like if it's like hollow shell, that is just expanding. All right, then it's just biconical.
Expansion will do.
Yeah. Yes. Yes. Yes.
So I don't understand actually. What do you mean by turbulence velocity? Again, this 100 you're saying?
So this is
What is velocity of turbulence?
so so generally, so I am using this term a bit loosely for like a more non-technical audience. So generally, if you say velocity of turbulence, it would be like the eddy speeds. All right. Now, yes.
Inside the
Yeah. Yes. 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 Now, this one, which we are measuring, is like the projected line of sight. This is the velocity dispersion of that gas motion, which is like you would have a distribution of velocities along line of sight. What is the? This is sigma v. This is sigma v. This is sigma v.
It's a figure for a proposal, right?
Yes. This was a mistake. This was but yes, we wrote in the caption that it is sigma v. So yes.
So if this is the velocity dispersion,
Yeah.
then how is that related to how fast it will move from some position to another position inside the cluster?
So it depends.
Sort of assuming that it is proportional. I mean, it's roughly the same order.
So yeah, so if there is a turbulence, some speed, all right, and if you multiply with the like how much the energy, like how long it would take that turbulent energy to get dissipated, you can roughly get a time scale. Sorry, length scale. All right. No, if you multiply by this sigma v, this velocity with the time it would take to radiate away the energy in the turbulence.
And what do you
So you have to calculate how much energy is there based on the sigma v. You can calculate how much energy is there, and
that I'm getting one length scale.
yes.
No, that is fine. He is saying that if you are dissipating energy at some rate, that you somehow assume.
Yes.
And then you say that okay, but this body is also having this random motion.
Not random motion.
Whatever. I mean, it's looking at a projected velocity.
But it is confined to a region. Random motion confined to a region.
Yes.
These are sort of splitting, so it's not really. It's not like one circular motion.
Not one circular, but they are not moving bulk-wise.
No, but the approximate
But-
distance
so-
covered will be the time scale times some velocity, right? So that is the velocity that you.
So the bubbles can rise through the atmosphere, and the wake of the bubbles can be transmitted around the atmosphere as well.
You are saying with bubble
Yeah.
that rise.
Yes.
That velocity depends on the shock velocity.
Yes.
How fast that shock moves. But the random velocity depends on the temperature of which is different.
Well, it's
Different
not.
velocity.
It's not temperature, but yes, they are two different velocities. Yes, but they are connected.
So let's move on.
Let's move on.
Let's discuss.
Okay. Yeah. All right. So okay. So sorry. Am I out of time? Okay. Okay. So this is so now I'm going to show you the results, the 5. So now I've told you why high resolution spectroscopy is important to determining this. I'll show you 5 clusters, all right, because that sounds like a good number. So first of all, we have the Centaurus cluster, the spectrum that I showed you before. So every cluster that I'm going to show you is nearby somewhat, because in the PV phase, we want to show clusters that are interesting, nearby, very bright, so we can clearly determine the physics that were chosen. I want to keep an eye on the AGN power as to how results may change or may not change, depend on. So Centaurus has a very low AGN power of 7×10⁻42 arc per second at the center. All right. With XRISM, those 36 pixels you saw were divided somewhere like this. I want you to also see the Centaurus has a merger going on along this axis. And there in Chandra, we have seen some brightness edge. around here. All right. Now, that is from like radio, I think.
That's from radio.
Yes. All right. So, and I think you can also determine based on these cavities, like cavity power, the mechanical energy. All right. So, and all right. So, how much is it, the turbulence? So, if you look at the turbulent velocities, well, forget about like hundreds of kilometers per second. What you are seeing is it's barely not even, it's about 120. All right. It's like a lot lower than what we expected. All right. And the turbulent velocity is not really even increasing as you go towards the AGN. Like it seems to be. So you can take spectrums and then fit the spectrums and measure the weights of the spectrum.
Constructors of the spectrum.
Yes, yes. So the turbulent velocity doesn't seem to be increasing with the AGN. First of all, it is very low. It's not like the hundreds of kilometers per second I was told, which is required similarly. And also, it's not like increasing near the AGN. In fact, what is happening is in bulk motion, like you see some like a blue shift in the Bay region, this sharp surface brightness stuff happening. What we think is happening is in Centaurus is like this as sloshing kind of motion. All right. So there is a merger going on. And after, like during the merger into this Bay region is like coming towards us. And any turbulent velocity, so this is calling a slingshot type of effect during merger. All right. So what is happening is that this sloshing motion is causing what the blue shift towards us, and any turbulent velocity we are seeing is really due to this sloshing effect and not due to the AGN. All right. And if you want to know what sloshing is, it's really like if you smash two wine glasses together, you see the wine like sloshing together. It's what exactly happens during merger. Like after the passage, it kind of slingshots. All right. And the gas is like sloshing in the potential well.
Even thumbs up will be.
Yes. Wine or thumbs up or whatever. Okay. So this was the basic picture that we constructed based on the turbulent velocity and bulk velocity data. So we can ask the question of, can turbulence by itself offset cooling in cluster core? If you do the calculations, it's about 3 times 10 to the 43 arc per second, where the length scale has been taken to be the core radius. It roughly matches the cooling, all right, produced by sloshing, not the AGN, by the way, in this case. But can it travel fast enough? You can see that the range is only limited to like few tens of kiloparsec, which is like the much less than the cooling radius. So AGN turbulence is like, not, this is sloshing turbulence, but it cannot really heat the whole core. Also, is it Kolmogorov in shape? So people have not done exactly the matching yet with distance, but you can kind of get an idea from here. It doesn't look like a Kolmogorov, by the way. It's like a really flat kind of velocity distribution. So like these 3 points from Centaurus, just like one data point. We can look at other clusters. So basically, it needs to like a decline. Length scale. That is the length scale. Yeah. So basically, the velocity needs to decrease with a radius. All right. So I'm just saying that although we have not directly done the studies, I'm just showing like qualitatively is like like there is no like decline, steady decline. Like it seems to be like quite flat actually.
But that radius is Lee's radius. That radius is not anything to do with cluster center distance or anything.
No, so you can also do that from like if it has been injected in the bay at the.
Suppose it was Kolmogorov,
Yeah.
what kind of figure would you see?
You would see so there's a gradient of like the velocity with the distance depending on where it was injected. like if it was injected from the AGN, then from the AGN, let's say the decline is, if it has been
is not in cluster frame. It is in the AD frame. So the same region I can have large AD, small AD, small AD, small AD, and how the energy goes from the last to small AD in that exactly the same region. It tells you what is going on.
Yes.
Not that this big one is over here, the next one is over here.
How big is
so the ADs, so the idea is that because bubbles produce these eddies, the length scale of the eddies is connected to the bubble scales. All right. And then it kind of, so it is connected like that.
So you say that smaller eddies will be the outer skirts. They are moved to the outer skirts and dissipating the energy there, and larger eddies will be near where it is the
injection site.
Near the injection site. That's why you get some kind of velocity distribution along the radius of the.
And what is the spatial scale of this velocity mass?
So this is like a 3 arc minute, but it's like 3 by 3 arc minute. So this is be like, oh, I have to remember. It's like like 20. Oh yeah, so yeah, it's about like 20-30 kiloparsec, I think.
Yeah, he showed the scale was there.
Yes.
Kiloparsec was half of the previous.
Yeah.
30 kiloparsec is very small.
Yes.
Yes.
It's
Yes.
the galaxy size.
Yeah, so I'm just saying that the turbulence is so low that it cannot really like propagate the whole cluster core. That's what we are getting. So we can also look at Perseus clusters of galaxies. So Perseus is the brightest cluster in X-ray sky. All right. It has a lot of things going on. It has a merger. It has an AGN, strong AGN at the center, which creates cavities. It has also some mergers going on at the larger scale. So what XRISM has done is like look at like 4 different pointings, which is directed towards the merger axis. All right. So you should see like effect from merger around here, as well as effect from AGNs in the center as well. What do we see when we do the velocity dispersion map? Well, first of all, it's like all over the place. All right. This is not surprising because like in the larger scales, we have like mergers going on. All right. And in smaller scales, we have like the effect of the AGN. All right. So you would need like multiple different injection scales to like even, so you can use a turbulence from the merger. So at the different scales to even reproduce the data. All right. And only in the center is where you have the turbulence from the AGN, which presumably is driving this rise in velocity dispersion.
Here's figure.
Yeah.
Each box is I can have a spectrum.
Yes.
Smaller square.
No. So sorry, I should have explained. So I think like yes, it's like the full one. Yes, I think like it's slightly smaller than full one, like because they have done something like this. Yeah.
So it's full spectrum.
Yeah, 4 to 5 because they have no. Yeah. Yes, that's you measured the velocity dispersion, and that's what has been plotted here.
But your everything requires going down at the center, which is not happening with the data.
Yes, if you only had merger.
Data points are your data points.
Data points are data points.
So what are the models?
Those are models based on scales. Yes.
I should go to a lower velocity dispersion at the center, which I am not being seen, so it cannot have the merger thing of it.
Injection radius means injection of what?
Injection of the turbulence, the energy, turbulence energy.
Injects some turbulence because everything is to the central agent.
Yes, here, but here. So I that.
See, I don't understand how can we
That's not AGM, that's the merger, is it?
This is merger. So two things are happening. So at smaller scale, less than 60 kiloparsec, we have like effect due to the turbulence due to the bubbles. All right, so that's the AGN is affecting it. Beyond 60 kiloparsec, it is merger driven. And then we are calculating like at what injection scale that merger turbulence would need to reproduce the data.
So then one thing I notice here that the green one, where the injection scale is 50 kiloparsec, which is pretty close to the core, and you can expect that to be the AGN-driven shock, AGN-driven turbulence. Am I right? The green guy. But then it's quite flat. I mean, so why is there a difference in the? So are you claiming that? I mean, why is the green flat whereas the ash and the orange one, they're much higher in scale.
So I think the 50 kiloparsec here, it's being only from here. I think it is being affected, and then cascading down. This is So this one, I think. I have to check, but they might just be doing like beyond the 50 kiloparsec. They're just keeping it, they're just showing it flat. But I have to check it. But
well, not necessarily. There are also
is going to heat up the outside
or not. How much can it?
This one doesn't say that. Sorry, this one says that over here. The injection is 500 kiloparsec, and that's what is only from margins. What do you do with AGN?
Yes.
And one thing is easy to understand from the model. If something is injected at some radius, the velocity dispersion will gradually die out as you go far away from the radius. So if it's injected at 500, slowly that maybe there's some flattening and then falls outside 50, it's gone down. The 100 also goes down, but slowly because your injection is less. Remember, the 500 has to be more. Also, I think.
Yep.
Because
otherwise it will completely.
It will never come up to this.
Yeah, it will never come up to that.
Okay. Something at 50 will probably not. I don't understand why it is not falling, but it can be that there is a slight slope. It's only the scale over here, which basically
which
is forbidding us, which is not allowing us to see.
Which it could be the case. I have to check this and go like exactly what they're doing here.
That being said, I do not understand what exactly again. So I don't understand it. So this is by what exactly I mean by injecting something at 500 kpc, injecting something at.
So it is that why you are making the shock.
It is where the turbulence here.
Shock is creating the turbulence.
At this length scale.
So that's not that shock.
That's due to mergers. That's due to mergers, the turbulence. No. No. What you are confusing? You are confusing merger shocks if you are confusing that with cluster formation shocks, then accretion shock, accretion shock or like virial shock, that's like much further away. What we are talking about, that Perseus is merging with subclusters, all right, and that is like much closer.
So it's a subcluster which is merging.
Yes. So like
injected by AGN. Versus when it's being injected by this merger shock.
Merger turbulence.
Merger turbulence. Is that a different model or what?
It's in AGN we do not know anything. The only way, if these are probably some from simulations or from some model. Model you can do, but with simulations, the only thing you can do is that you can think of some bonded radius and deposit all the energy of the AGN with some fraction into the bonded radius. And then whatever energy is deposited over there, then you let your SPH or whatever equation.
Here we are not doing anything like that. So here what we are doing is, what if we deposit energy at some scale, and what if it cascades down according to Kolmogorov? We then use the projections and like see what the velocity dispersion should be.
Then the normalization is too high. I mean, if the 500 kiloparsec has to run all the way up to 50 kiloparsec, it has to have much more high, because I can see that the orange is much higher than the green. I mean, right? Am I right or not?
Yeah.
I mean, when you are injecting the, but this is all because the data shows that. That's why you
So
match the data into it.
yes, to like the injection scale needs to be far higher to like for it to cascading and match the data. Yes, that's what I'm saying. Like within the 60 kiloparsec, like this portion is mostly due to the AGN. This part is mostly due to the merger driven, is what I'm saying. All right, so we can play the same game again with Perseus. Like can turbulence itself like heat the cluster core? All right, so based on those 5 data points, people have calculated like the heating. All right, like so this is like the cooling curve, how much the cluster is cooling versus how much is being heated by the turbulence. And the way we are determining the L effective is like what is the effective length of the cluster along with the projected radius. So you do integral of R times emissivity, which is like how much emission is happening, divided by the integral of the emission. So you have like an effective length of the cluster along projected distance. And this is like the effective length scale of the gas motions. All right. So at very low radius, the effective length of like the parcel of gas that is moving is like low, and as you go outside, because the emissivity is quite low, so the effective length scale is also increases. This is like the idea of the effective length scales.
Length of what? Physics wise.
So this is the exact turbulence length scale. All right, is like is far less than the XRISM's resolution. All right, spatial resolution. So what this length scale is basically like an average sort of gas motions like at each radius. So like what you are saying is like what is the like if you have a parcel of gas that has been affected by turbulence, like what is the like average length scale from the center as a projected radius?
We can talk about that later. Please wait.
There are lots of questions.
Like so many.
All right. So okay, I'll just move a bit quickly. So it like a lot of the data points what we find is like going below the cooling curve. All right. So here you can also assume like maybe the effective length scale is only of the start of the bubble, which we cannot probe with XRISM, like that small scale. If we assume that, we can boost it. So we have given a range. But if you want to be self-consistent with like effective length of like each projected distance, then a lot of the data points is like below the cooling curve is what the picture is emerging. Can AGN turbulence travel fast enough? If you can again calculate like how much of this energy, how this energy would be radiated away, how much cooling time, how much time, and make the calculation. It's about only 20 kiloparsec kind of again, which is again very below cooling radius. So again, the picture is emerging that it cannot travel fast enough, all right, before being radiated away. And is it Kolmogorov in shape? Well, previously you saw like it's like the dispersion is like all over the place. All right, it's unclear right now whether there is Kolmogorov because there's so many drivers or not. So this is still like so far it's not emerging to be Kolmogorov, but that could be due to like a lot of effects present as well. Okay, I wanted to show Hydra A results as well. So Hydra A is one of the very powerful AGNs. Now we have boosted the power to like 210 to the 44 arc per second. So 42 to 44 arc per second. And we have basically these two pointings. And the reason they are chosen was because there's really big bubbles of Hydra A that were present. All right, and so we wanted to see like how much energy this is being deposit, like how it is being affecting that. So the dispersion is quite interesting. So first of all, even though we have boosted the AGN power, you see that the velocity dispersions remain quite low, about 160. So like there seems to be like not the dispersion is not being boosted. Huh?
This dispersion is coming from this bright spot or the dark spot?
So this dispersion, so we have divided from these 2 points. So this one is from this one. So this one, this data point is coming from this one. Yes, yes, yes.
It's coming from the gas, the
So-
bright side or the dark side?
Well, it's all mixed together.
Don't know that.
Yes, but it has the big bubbles. Which yes,
Hard to say.
It's very hard to say which one you are probing.
it is like probing this yes, this big this big bubble part of it.
In a sense, right? If suppose the whole thing was black, then you should have expected more or less. It's not getting up to that point. The whole thing was white. So in that sense, you can say whether you are expecting.
No, but it's the dispersion. It's not the actual
So-
normalization.
So yes, so it is partly due to the cavity, partly due to this gas as well. All right. So the point I'm trying to make here is that even though we have increased the AGN power, the velocity dispersions remain quite low. And more surprisingly, this has remained quite flat as well. All right. So the reason for that is could be due to the expansion of that the bubble is injecting additional energy at the larger scales, which is preventing it at additional energy.
Where
No.
is the center of it?
Here.
Center is there.
So like there are multiple bubbles in hydride.
Two-sided bubble.
Yeah, okay. So if you do the same kind of energetics calculation, and do the effective length, I'll go over this a bit quickly. So you will find that it is only about 60% less than the cooling luminosity. So it cannot actually balance cooling in Hydra A as well. If you want to make it match, you need about 13 kiloparsec injection length scale, which is like very small. Yes. Now it could be possible because the bubble like encompasses the whole a lot of the central pointing. It could be 13 kiloparsec, but we just don't know yet. Like you need a very small length scale to make it, but the bubble sizes are much bigger, I must say. All right. So it appears that it cannot balance it. Okay. And why not Kolmogorov? It's presumably due to bulk motion, like at the outskirts, for example, like there's a large bubble that is being expanded, and it is possible that is adding much more energy. All right, that is what making it go flat.
Yeah, it's very hard to say.
I mean,
because-
other than the first claim that it is not very high, anything else is not actually taken, not a grain of salt, but like a big bowl of salt.
Well, I mean, so I think like, yes, like it would be like consistent with, I think, within 2 sigma or something. So for now, this like that, this is 1 sigma.
It's just
like you can even feel it's like going
I mean, only
beyond
thing you
the
can really say.
Yeah.
I think it's an interesting thing that any of the points is not like 300.
Yeah.
Yes.
Right.
That you can say.
Yes.
Even with 2 sigma, it's less than 3 sigma.
But everything else saying that, okay, this is the size of the thing, all these are too much of an extrapolation. I would be very skeptical of that, or I would personally not brave enough to do it. Because I don't.
Yeah, okay. Fair point. So I had 2 more clusters, but like I will run over briefly, skip over it. I will just go to my like the brief takeaways. All right. So like, is there any trend All right. So we have a sample of clusters that we have now observed with XRISM. And if you observe the if you have jet power on the x-axis and sigma on the y-axis, this is what you get, like a total scatter plot. Like there is no trend. So with Chandra, you had like cavity power and X-ray power. They're like very strongly correlated. Like, a lot of scaling relations were there. So far, no scaling relations are emerging. Now, you can also ask, well, Onnesh, that's very obvious because a lot of these clusters have very different footprints with XRISM. All right. So maybe you're just looking at different, comparing apples with oranges. So you can divide the mass that has been there in the XRISM footprint and divide that out. All right. So you're seeing how much energy is there per unit mass. Okay. And even there, like a lot of these things have like no like clear correlations between jet power. So far, it is emerging, which is very interesting. What about like the velocity dispersion with respect to the radius? Here also, like it's because of the large error bars again. It's only tentative, but a lot of them have shown declining stuff, but some of them have shown like very flat. They become very flat. A lot of them so like increasing, some one or two of them, and some of them just show flat. So there's like no consistent kind of pattern. It's like it is consistently declining with radius. So like it appears to be that the Kolmogorov scaling is not obeyed in clusters. Why is that so? So in my takeaway messages is that the velocity dispersions are like low. They're not high hundreds. All right, they're like pretty much in the low hundreds mostly. They cannot propagate through the cooling volume. All right, so they cannot. So if they want to travel the whole cooling volume, they must be produced in situ, because otherwise they'll simply be radiated away before they deposit their energy. In many clusters, it seems turbulent heating cannot balance cooling. There are obviously caveats to that. We have uncertainties on where it is being injected. So there's some uncertainties on that. Why is it not Kolmogorov? It could be that unresolved bulk motions could be affecting our measurements. Like the dispersion we are seeing, especially with like Hydra A, that outside. A part of it could be like expanding bubbles as well. That has affect our velocity dispersion measurements. So that needs to be figured out as well. So we need to observe more away from the bubbles, let's say, to see if like the scaling relations are being maintained or not, so that we have build a bigger sample to see if we can generalize this to takeaways and see a consistent. So, but these are so far the picture that is emerging from XRISM. So I'll just end it there.
So we have like lots and lots of questions for Anish, but yes, if there are other questions, Abhijit, please.
You said that the cavity is using the AGL feedback method to kind of propagate light towards the galaxy cluster, right?
So what are the two?
Yes, please repeat, Abhijit.
Okay, I am saying that a galaxy, as you said, that there is intricate balance between heating and cooling.
Yeah.
And cooling is happening because of the electromagnetic radiations we are getting.
Yeah.
The energy is getting outside the system.
Yeah.
While the heating method is kind of it's happening on inside the system. So as time passes, it will still collapse, right?
No, cooling is through radiation.
Cooling is through radiation.
But that energy is outside the system.
Yes.
But while the heating is only happening inside the system, so in enough time, won't the galaxy cluster still collapse?
You are converting the energy that is so. So the energy. So you are converting the part of the matter, which is being accreted to the black hole. Once it is cooling enough, like when it is accreting matter, it is then using the matter to like produce the energy, and so that that can then keep the thing balanced.
Yeah, but concept, right?
Total energy is conserved, so that's all.
Yeah, but the energy, the cooling method, the energy is going outside the system.
But inside the system, you are pumping some energy and taking away some energy. So in the system, the energy is
So-
conserved.
Can I?
Yes, please.
Yes.
So you have gas, right? First of all, the cluster is, one thing I should, cluster is always collapsing. Yeah. Slowly, doesn't matter. There is gas. The gas is cooling inside. The gas is cooling. How the gas is cooling? Because it's emitting radiation. X-ray is going on, water, something else is going on. It can be other stuff also. Emitting it. So locally the gas is cooling. When the gas cools, what will happen is what you said is right. It will collapse. The gas will collapse.
Yep.
Okay. So gas can go from the gas phase to a non-gas phase.
Yep.
And can,
Emit stars.
and can be out of the system. So the system, total mass is still conserved. The only thing is the mass difference in gas has now
Yep.
become mass in stars, let's say. Yeah. Now, locally, I am feeding energy. Okay. This energy is fed by what? It's fed by the central black hole. Let's say, take one example. So whatever gas is going inside the black hole, it is being thrown out with some energy. So the black hole converts this gas in presence of the magnetic field into some energy. Okay. A fraction of the energy comes out. And that energy can be enough to balance the cooling. Okay, if it balances the cooling, the gas doesn't cool anymore. So the gas stays as it is.
So I understand your question. So you are saying the total energy, you're worried about the total energy. All right. So the total energy, like, it can be added. So through mergers as well as additional energy mass can be accreted into the clusters. All right. It's not. So it's not like clusters are not closed boxes. All right. They are interactive. It's like the total energy.
There is one. We are creating energy in this black hole.
Yes.
A small amount of mass in this mechanism.
Accretion.
Accretion is giving you an energy. So
Yes.
it's not that over the way there's a balance, is there some energy is already lost, so total energy is going to no. I have added some new energy.
Correct.
That
Yeah.
energy was mass before, but this mass is very small. Okay.
Yeah, this mass
That
is
doesn't
small.
go in the mass balance. Of course, it accretes matter. So black hole accretes mass at
I think
100.
he's also I-
Only a fraction of that gets converted to energy, and a fraction of that comes out. So there are many fractions going in.
Yes.
So
There
yeah,
is enough to balance the energy locally, but the mass balance is not affected.
yeah. So like the mass is like very small compared to the total mass. So it's hundreds of solar mass per year that is kind of accreted, let's say. And then yes. Now you can imagine like some infinite time later it might be a problem, but then like it can also be like energy, as I said, energy can be added to the system by mergers, external accretion shocks. So like it's never going to be a problem in this way. Yes.
Okay. Next, any other questions from anyone? Any other questions? Okay. Okay, quickly.
Again, my question, I don't know
Okay.
how the turbulence is happening today.
Uh-huh.
Pure turbulence.
Uh-huh.
Is it that the place where you are creating the turbulence
Yes.
is hitting that region, or it can propagate?
So it can propagate as well. So
Where? It can propagate.
whether
At what speed?
yes, so it's generally a function, like a function of that velocity dispersion. It's not exactly the velocity dispersion, but it's related to the velocity dispersion. Yeah.
Must be much less than that velocity of the turbulence. Yes.
I mean the propagation
Turbulence
speed.
hitting is a viscosity.
Discuss it.
So
Yeah.
the propagation is sound.
That's
Propagating
what
at a
sound
sound
speed of the cluster.
Sound speed, which is much smaller than this.
Now sound speed is much larger than that. It's about 1,000 kilometers per second because it's about 3 kV, 4 kV plasma. Yes, hot.
Hot,
Yeah.
hot.
If it is propagating at that speed, then why I need to do all these calculations to find out whether that can be a cause of turbulence or not. Turbulence.
No, I think it's talking about the scales. Right?
So if I need to know the
So
velocity.
your point is that if the turbulence that propagates at the sound speed, then what is the question?
I think turbulence.
Because energetic was not at all a problem, never. Energy was always there. How to propagate from the center
To the bigger scale,
bigger
the length scales.
bigger
My,
length
my
scale.
simple understanding question, which I don't understand properly, is that let's say when I do take a system that you have done our own galaxy and you have calculated turbulence in our own galaxy and see whether it's cosmogonic spectrum or not, it is more or less cosmogonic. Right. So what you do, you want to estimate the turbulence at certain scale, small scale, like let's say sub-parsec scale, and you do that with different regions. If it's good, over the entire sample of the galaxy, if it's not some region and say that's a good enough, representative sample, then you increase the scale and then again do it, then you increase the scale and then again do it. Okay.
Yeah.
In that sense, you are getting, and then then you can see whether this turbulence at the different scales, the average turbulence over here, different scales, whether it has a cosmogonic spectrum. Over here, the size, when I say cosmograph, is again at the scale at which I am doing turbulence. This scale, this scale, this scale, this scale. It is not like something from a center.
It doesn't allow me why the
Over here,
injection
the turbulence sigma as a proxy for turbulence is shown as a function from the center in the last picture that you showed. So over here, I don't understand. If you are doing at small scales in the galaxy cluster, saying, okay, this is at this scale, this is a turbulence energy, and this scale is a turbulence energy, this scale is a turbulence energy. That is different from saying that turbulence energy is going away with the function. And saying that can be done, but
yes.
But connecting that to cosmography, I don't know. You can always calculate turbulence energy at any scale
Yes.
from the center and plot it as a function of radius from the center.
Yes.
That is fine.
Yeah.
Saying that spectrum
like you can, so what you can say like is if it was only if it was only like injected by one, like say in one burst, and then and then it cascades down, then it should follow Kolmogorov, right? Like you inject it at some, so you create eddies, and then that eddies like cascade down, all right, then it should have followed Kolmogorov. So what we are saying is probably it's not, even if it's even if it's turbulence, it's probably not like a single injection, like if you have to produce in situ to.
What maybe people are trying to think that as it cascades down, size becomes bigger. If it's TBS at the center, the size becomes bigger, is like the size of baby, and so then as a function of size, I can calculate this. That probably is what you're trying to say, but I mean, I don't know.
I think the basic idea is something like that.
So again, it means if I have a dispersion, dispersion velocity, and I take that the velocity acquisition,
that is, yes, like
it can move the
yes,
length.
yes.
And if I multiply by the time scale, it doesn't matter.